Hello, my name is Jo van Bulck from the Dissonant Research Group at KU Leuven, and it's my pleasure to introduce you to our research on Pandora, which is a new symbolic execution tool to validate so-called Intel SGX shielding runtimes. So this was a joint project with the people listed here on the slide, so from both the University at Leuven and the University of Birmingham. Let me start at the start. What exactly is Intel SGX? You can think of SGX as a fortress inside the processor that allows you to execute code and data in complete isolation from the remainder of the system. So that's clearly a valuable asset, but if you've been at some of the system security conferences in the last decade, you've also seen that SGX has been a very popular target for attacks. And many of those attacks, not all, but many, have abused the software interface. Very similar to how these Vikings here tried to enter this castle to the weakest point, namely the interface at the gate. And just as a case in point, you see here a number of vulnerabilities in the Open Enclave project from Microsoft, where you see over the past 5 years a continuous stream of vulnerabilities in the Enclave interface. Just to put that a bit more into perspective, this is the bigger picture. You have an enclave, a fortress in an untrusted world, and the question is, how do you securely enter or leave that fortress? And we've seen essentially more and more requirements being imposed on the programmer on lower and lower levels. So that starts at the level of the program visible state, where of course the programmer is responsible to clearly handle pointer arguments in the shared address space, but also at the level of program invisible state, so CPU registers, which have been repeatedly abused to modify the behavior of the protected program. And even at the lowest level of the microarchitecture, again, not all, but many defenses rely at least on partial help from the program to insert certain cleansing or serialization instructions to help defend against these attack surfaces. So what all of these levels have in common is that the key question is, how do you bridge from an untrusted world to that secure enclave world on the other side and back? And for this kind of bridging, the term enclave shielding runtimes have come into use, which essentially build that bridge, as is shown here in the yellow, by transparently interposing every entry and exit of the enclave application and sanitizing things like pointer state, CPU registers, and even things like a small initialization and runtime library. So these things really make the life of the programmer easier, and as a result, we've seen a large amount of these runtimes being developed when this technology has matured over the years. So you see big names like the official SDK from Intel, also Open Enclave that I mentioned before, the Grammine library operating system, and so on. And essentially, the starting point of this research is to recognize that all of these runtimes form an ecosystem. See that ecosystem being summarized on the left, where essentially different programming abstractions have been supported. One is at the abstraction level of just function calls, which is the typical SDK approach pioneered by Intel and Microsoft, but also at the level of merely shielding existing applications, legacy applications, which is this library operating system approach pioneered by things like Graphene and Grammine. And in the middle, you have language-specific runtimes that are, for instance, the support in the Rust compiler to transparently compile Rust applications to SGX enclaves. And the starting point, again, is that we recognize that prior works have mainly focused on the application tier here, and to be even more specific, applications that were developed on top of the official SDK from Intel, which, as you can see, is only a puzzle piece in the larger ecosystem. And so the goal of Pandora is to explore that ecosystem in more breadth. And essentially, what you see here are the yellow 11 runtimes that we analyzed. And you can also see that we very consciously decided to not investigate applications. We recognize that applications are also important. Validating application logic is also important, but validating shielding runtime logic is more important in the sense that any vulnerability in a shielding runtime can be exploited in all of the applications running on top. So it's essentially the equivalent of a zero-day rootkit in a normal application. And so our effort has been trying to cover all of the root runtimes on the left. While doing that, I think we also bring two novelties that I want to highlight further in the presentation. One novelty is an inherently runtime agnostic way to extract a binary that truthfully represents the actual enclave being executed, and so more accurately allows symbolic execution to proceed from the very start, including low-level initialization code. And secondly is an approach to deal with the complexity of this moving target nature of vulnerability detection, and allows to easily add new types of vulnerability detectors by means of plugins. So let's start from the first. How do we go about this notion of truthful symbolic execution? Very briefly, something on symbolic execution. I won't go into too many details, but it suffices to say that we build on top of a mature symbolic execution library, the Anger library written in Python. I can very much recommend working with Anger. It's a very quick way to get started with symbolically executing x86 binaries. The key idea behind symbolic execution is to simulate a program, so to not actually execute it with concrete inputs, but on every control flow or data flow decision to branch off all possible state spaces of the program. And you can see that being illustrated on the program, the simple program on the left, which is essentially an enclave that takes a pin code and either returns 0 or a secret if the right pin code is given. If you would execute that enclave with a tool like fuzzing, you would essentially suffer from the big state space, and you might never find the secret. But if you take this more principled approach of symbolic execution, you can see on the right the search tree being built, and with the help of a simple constraint solver, it's very easy to see that the pin code would leak immediately. So that's a starting point, but of course not the ending point. So we very quickly realized that Anger is not designed to run Intel SGX binaries. Instead, it's designed to load normal operating system binaries, and that brings two main challenges. One is that SGX binaries are very runtime specific, so they often disguise as normal ELF operating system binaries. But essentially, they have to be loaded with a very involved process where you talk to the driver, which in turn talks to the hardware and builds the expected layout of an enclave one by one, as you can see illustrated on the left. So there are things in there like thread control structures and safe state areas, also more conventional things like stacks, heaps, and code and data, but they all have to be in the right order and in the right place. The initial layout, the one being illustrated on the left, is also attested to the remote stakeholder. So essentially the hardware, the SGX hardware, will compute a cryptographic checksum so that the remote stakeholder knows for sure that the enclave has been loaded correctly. So we need a way to bring that into Anger. We'll come back to that in a second. Secondly, we also need a way to deal with untrusted vault interactions with normal applications that's quite clean and clear, and that's our system calls. And Anger again is optimized for the system calls, but in the case of SGX, you typically have to enter and re-enter the enclave to handle this kind of behavior. And we also have to deal with that as we will see in a second. So the starting point, as I said, is to put your binary into Anger. It will not work out of the box, and prior solutions have come up with some sort of ad hoc approaches that are very specific to the Intel SDK, sometimes even to a specific version of the Intel SDK, to essentially get a binary in a form where you can start executing it without executing the runtime. We are inversely interested in executing the runtime. So instead, what we have found is an approach that executes the untrusted loader once and hooks into the driver by means of ptrace. So we do a simple fork followed by ptrace, which means that we can listen to all the system calls to the SGX driver, and we can follow all of these individual phases that create the enclave. Every individual page that's being added, we keep track of that in a byte granular memory dump. That's perfectly correct. And we also keep track of layout metadata such that in the next phase we can perfectly reconstruct this Mr. Enclave attestation value of the initial um, perfect binary layout of the enclave, which includes its boundaries, entry points, thread local data structures, and so on. So that is the starting point for our symbolic execution. We load that into Anger. We have sort of a custom Anger loader to do that. And then, as you can see, between Anger and our loading phase, we also have this component that we call the engine, which takes care of all the Enclave specifics that Anger is not aware of. So things like the behavior of x86 instructions for SGX, but also a powerful taint tracker and re-entry mechanism. And last but not least, an Enclave-aware symbolic memory model that is, I think, very neatly integrated into Anger and could serve as a foundation for future work as well. So at this point, we have garnered all of the architecture and machinery to make that work, but we have not found any vulnerabilities yet. So let me also say something about that. So the way we go about vulnerability detection in Pandora is by means of this top right component here that includes essentially a pluggable vulnerability detection scheme. So we have 4 different plugins for 4 different vulnerability types, as we'll see shortly. And the way that works is that the engine exports certain interesting events to plugins who can subscribe to them and sort of use that for vulnerability detection. So what I want to do is to zoom in a bit on 2 interesting plugins, the pointer sanitization plugin and the ABI sanitization plugin. And let's start with the former. So what's the actual problem of pointer vulnerabilities in Enclave programs? I said earlier that Enclaves execute in the address space of a host program, and essentially that means that attackers can address Enclave memory but cannot access it, and vice versa. Enclaves can address and access the whole address space, including untrusted memory, which allows for fast copying of arguments. And what you can see here is a very simple enclave, arguably the simplest enclave. It will take a pointer to an untrusted string in untrusted memory and just pass that back to the enclave who prints it, to the attacker who prints it on the screen. What can go wrong here? Well, what if the attacker modifies the pointer to point to a secret location inside the enclave? And again, without proper care, the enclave would dereference that, even though the attacker cannot see it, and return it to the screen to the attacker. So that's an example of a confused deputy attack that can be extremely tricky to find and mitigate in practice. Just to give you an idea of how tricky it can become in practice, here you see an example enclave a bit more complex with a composite argument, so a struct argument with 2 values, an integer and an address, a pointer. If you want to securely handle that, you would have to start by copying the full composite struct by checking that the full composite struct lies outside the enclave. That already means that you have to deal with pointer arithmetics, which can be quite tricky to do in practice as well, as we found out using our tool. The second thing that you would have to do when you deal with nested pointers, it becomes more complicated because you have to copy them inside the enclave to prevent time of check to time of use before finally checking that they too lie outside the enclave. So this is just an example to show how real-world programs can become extremely complex, and we've seen time and again in our work and in prior work that dealing with these pointers is extremely sensitive and tricky, and we need principled automated tools to find them because humans will overlook 1 or more of these checks. The compilers can also compile them away, as we have seen in a couple of interesting instances that we describe in the paper. Similarly, at the level of the ABI, there is a vast amount of complexity involved. Even the basic execution environment in x86 has different configuration registers, like obviously the stack pointer, but also the rflags register that can change the behavior of different instructions in unexpected ways. And essentially, the enclave has to ensure that whenever you enter the protected execution environment, these values are sanitized. So prior work has shown abuse of these two registers, but also subsequently for the x87 floating point unit and vector extensions, configuration registers have been abused and need to be cleansed on entry. Most recently, Intel even released a refined version of MXCSR sanitization for mitigating against timing attacks. So again, this is a moving target that keeps changing, and we need principled tools to find out if these sanitizations have been applied correctly. So the way we deal with that in Pandora is through the notion of invariants. So plugins will maintain certain invariants and can subscribe to breakpoints exported both by Anger and by the Pandora engine to listen to events like whenever the enclave is entered or exited, whenever a pointer to interested memory is being accessed. They can check that, for instance, the taint rules allow this access. If not, then we recognize that as a vulnerability, and there's a nice reporting interface that can build interactive, rich HTML reports for further human analysis. Just to give you an idea, and the key question, of course, is what are the invariants? How can you do this in a principled way? What we found for the ABI, so for the level of CPU registers, is that all control registers should not be tainted by attackers when they are being read. So that's more principled than a block list or an allow list. Similarly, for the level of the API for pointers, we make sure that all addresses, all pointers that are even partially tainted by the attacker should lie fully outside the enclave and cannot partially lie inside the enclave. Again, has been shown to be a powerful rule in practice. And for this memory mapped IO alignment issues, we similarly check alignment and cleansing instructions. And for control flow instructions, we make sure that the target is not controlled by the adversary. Of course, the proof of the pudding is in the eating, and in fact, we launched our tool on a large number of runtimes in the ecosystem, 11 in total, and we found over 200 locations in the code that are vulnerable. You can see that our selection includes production runtimes as well as academic runtimes and closed source as well as open source runtimes. All of the details, of course, are in the paper, and we invite you to look further into them. Just to close up, I want to give you an idea of the type of reports that Pandora can produce. So essentially, I mentioned that plugins can register their info in HTML reports, and you can see here the header of such an HTML report generated by the pointer sanitization plugin. And you can see that it starts with a brief summary of the issues found and their severity level, and then when you would zoom in, you see the exact details of the vulnerability, how the taint has been propagated, and so on. And you can click open a disassembly and a full dump of the CPU registers, as well as a full log of the trace in terms of basic blocks, how to reach the vulnerability. So we ourselves, as well as the companies we worked with when disclosing these vulnerabilities, have found that extremely helpful to do triage. So in conclusion, Pandora represents the first truthful way to do symbolic execution of SGX enclaves, where we make sure that the binary is exactly the binary that is being attested to the remote stakeholders. We support the notion of pluggable vulnerability detection, where we implemented 4 different plugins. And in our evaluation on the SGX ecosystem, we looked at more than 11 runtimes and found a large amount of vulnerabilities, including in low-level initialization and relocation logic that has been ignored in prior studies. And then finally, I would invite you very much to look at our code. We built Pandora in the hope that it's useful for other researchers as well. We hope that this is not just a validation tool, but a validation architecture to add new functionality to. So you're very much invited to have a look at our GitHub page and feel free to fork the code, open issues, or pull requests in case of further issues. So thank you very much, and looking forward to answering your questions.